Hello, welcome back. Welcome to our first online lecture for the remainder of the semester. Truth be told, I do really wish you guys were here with me. I wish you were here just to discuss things with. You could ask me questions. But this is a very strange time, and this sort of social distancing is a necessary consequence that we all have to deal with. That said, if you do have any questions about anything from the lectures, please feel free to email me, and we should be able to get it squared up. But anyway, let's get started today. I just want to do a very short lecture today, a very short lecture for a couple of reasons that I discussed on Canvas. One is you have a test tomorrow, so I don't really want to start any new material. And two, I'd really like to just get us warmed up with this new video format. So luckily we can sort of do both of those things by coming back and discussing this relationship that we haven't talked about between transition matrices and diagonalization. So I'll recall exactly how this works, right? A transition matrix. Oops, can't write. A transition matrix P from B coordinates to C coordinates is the following. If I start off with a vector v written in B coordinates, and I want to then express the same vector in C coordinates, all I have to do is left multiply by p, right? So if I left multiply v in B coordinates by p, I get this new vector, actually not a new vector at all, the same vector v, but written in C coordinates instead. Right, this is the most important fact about transition matrices. It's how they work, and hence the name. You transform a vector in one coordinate system to another coordinate system just by multiplying on the left by p. Right? The second most important fact is we talked about exactly how to build this with this matrix P, and the columns are the vectors of this ordered basis B in C coordinates. So if you want to build such a matrix, all you have to do is take all your vectors in B and express them in C coordinates, and then place them in the columns of B, respecting the order of the fact that these are ordered bases. And that's really all you need to know, minus a little bit more transition matrix algebra that we discussed last class. But for today, I think that should suffice. And secondly, let's recall diagonalization. So A is diagonalizable. What does this mean? If and only if. It's really a definition, but I'll write as an if and only if statement. If and only if A can be expressed in the following way, as P times D times P inverse, where D is a diagonal matrix. Right? So A is diagonalizable if it can be expressed in this way. If it's sort of almost diagonal, but it's off from being diagonal by I've got to do this conjugation process. I've got to left multiply by P, right multiply by P inverse, whatever P actually is. Alright, so there's our definition. And what is P actually? Well, it's going to have something to do with transition matrices, hence the use of P in both cases. But we had talked about how to find this, right? How do you find P? Well, you go through this diagonalization algorithm we had, which is, what do? You find all the eigenspaces, and then you extract what we had called these fundamental eigenvectors from the eigenspaces, right? But what are those fundamental eigenvectors? Now that we have new language, we can talk about what they actually are, right? They're bases. They're basis vectors for the eigenspaces. And it turns out that if you sort of take them all, right, we take n of them to form as our columns for P, if you take them all, they're still linearly independent, right? So the columns here are n linearly independent eigenvectors. Eigenvectors of A. And what does that mean? Well, they're vectors in Rn. I have n of them. They're linearly independent. That means it's automatically a basis, right? So this gives a basis B so just by taking the columns of P, if I take all of the columns, I now get an ordered basis B for Rn, because they must be linearly independent, and I have n of them. And the dimension of Rn is n. So, I'm going to make two observations now. They will require a little bit of thought, but this is a vector, sorry, this is a matrix whose columns are the vectors in B written in standard coordinates, right? So what are the columns of a transition matrix? It's the vectors of B written in C coordinates, if you want to go from B to C. Here I've got the vectors of B written in standard coordinates, so this must be a transition matrix from B to S, the standard coordinates. All right, so P is the transition matrix. P is the transition matrix from B to S. Again, this requires a little bit of thought, right? It's a little bit unusual to think about it in these terms, but this is really what's happening, right? If I just take a bunch of vectors in B, and I make a matrix where they're the columns, I make a square matrix where they're the columns, then you always get a transition matrix from your basis to the standard coordinates. And a little bit of transition matrix algebra that we didn't discuss was, this means P inverse is the transition matrix from S to B, right? If you recall that from the week before spring break. So P inverse is the transition matrix from S to B. And the only new thing we've done today is really those two observations right there. Right, thinking in terms of this matrix P and P inverse as a transition matrix. So what does that mean? Well, I'm just going to draw a diagram now, right? So we've got a vector V, a vector V living in standard coordinates, and one thing I can do is I can multiply by A, right? That gives me the matrix, or sorry, the vector A times V, right? This will always be a vector still in Rn. But what else can I do? Well, I've got this relationship here that says multiplying by A is the same as multiplying by P inverse, then D, then P. So I'm going to build a diagram where we do exactly that, right? So I take V and I multiply by P inverse. That'll give me P inverse times V. Right? Next, I can take this guy and I can multiply by D. And I'm going to need a little bit more space. I'd like to save this word though. A diagonalizable. So we can multiply by D, and that's going to give us this ugly expression here, D times P inverse times V. Right? And last but not least, since multiplying by A is the same as P inverse times D times P, last but not least I can multiply by P. So, let's see, multiply by P to get back up to here. So A times V is the same as P times D times P inverse times V, right? That's just what it means to be diagonalizable. That I have this diagram. And of course, P is an invertible matrix, so I can sort of go both ways here, right? I can reverse this and say I'm going to go backwards. So multiply by P inverse, and over here I can sort of, instead of going down, I can go backwards and walk up. And here I've got multiplication by P. Alright, so this is just a diagram created using this formula, right? This expression for A in terms of P times D times P inverse. But these new observations give us sort of a different perspective on what's happening here, right? P inverse is the transition matrix from S to B. So here when I took v in standard coordinates and I multiplied by p inverse to get p inverse times v, that's actually the same as v in b coordinates. Right? And then we took this and we multiplied by d on the left, right? So multiplying by d on the left is really the same as d times v in b coordinates. So we've sort of, in my mind, and this is the way you should view this too, is we've got upstairs, everything up here is in s coordinates, right? Everything up here, that's happening in s. Everything down here, that's happening in b coordinates. And it's the same process, right? I'm just taking the vector v in s coordinates and multiplying on the left by a, and down here I'm taking the vector v in b coordinates and multiplying on the left by d, and I'm really getting the same result. They're related just by multiplication by this transition matrix. So the way you should be thinking of this diagram here is saying that d is just the b coordinate version of a. And so let's write this down. And in some sense, d is the b coordinate. D is the b coordinate version. I don't like that s. The b coordinate version of a. Right? What I mean by this is that multiplying by d in b coordinates is the same as multiplying by a in standard coordinates. So this is how they're related, right? They're related just by this change of coordinate systems. And in some sense you can, again, think of this as A is diagonalizable, so it's not necessarily diagonal, but it's not a failure of it to be diagonal. It's sort of a failure of the coordinate system you're working in. If I were just to work in B coordinates instead, multiplying by A is the same as doing this multiplication by a diagonal matrix down there in this new coordinate system B. So there is this nice relationship between transition matrices and diagonalization, right? And the relationship is right here. Is that A and D are related through this change of coordinate systems. But anyway, we'll start on chapter 5 next time. We'll get into really the bulk of all of this stuff. Everything we've done so far, we can talk about functions between vector spaces, which are super important.